Thank you very much. This is the part of the PhD dissertation of Aakash with my student, Ankit Gupta, another student from India, and the group from Bar-Ilan University of Professor Yosi Shor. I'm Professor Yosi Shacham-Diamand from Reichman University and Tel Aviv University. And today I try to make it in time because I'm between you and freedom. So I will make it very specific. We are making biosensors using synthetic biology, which is what is called plant-based sensors or whole cell sensors. They are working very well. We are doing it for 20 years, and there are also some companies now using it, so it's not something totally crazy. It's working. It's a lot of research. The main problem is that if you are an engineer and you want to design a system, you have to run these 3 different simulations. You have to run the biology simulation, all the DNA, RNA simulation using, we have simulators for this. Then you have to do, if you use electrochemical sensors, you have to do Butler-Volmar equations, diffusion equations. You run your own simulator using COMSOL or I don't know, something. Then you want to integrate it with the CMOS. You go to your Cadence or Synopsys and design your CMOS. And then you have to put everything together. This is what we do for the last many years, and it's a lot of work, and every iteration can take, you have to find the right person, and the technician is in vacation, and it's too much trouble. So we try to put everything on one platform. So the talk today is, and again, we decided to put it on Verilog-A because it's available on Cadence platform. It's standard in the industry. Warning, it's not the best, and it's a one, but I want to show you how it works, how we simulate, and I'm going, at the end of the talk, I'm going to show one simulation using a Verilog-A for everything, and mostly for the electrochemistry. I focus today on electrochemistry, but we can do the same for other approaches. So the goals is accurately model and simulate test devices and the seamless design of sensor interface circuits, integrate electrochemical sensor for high performance and low power electronics. This is another talk, not today. And modeling nonlinear behavior with memory effects using standard electronic components and simulation frameworks. So the method that we do, we use standard VLSI design tools. And Verilog-A was chosen as a hardware definition language. And we found out, and it's not a secret, but it's hidden in the catalog somewhere, that in Verilog-A, there are math functions. And you can actually write math functions and very complex mathematical functions, and then you can package it and like a subroutine in the good old days when we used to write software, and have like, if you define electrochemical cell, have 3 inputs, working, reference, and the counter like in a black box. And in the black box, you have all the modeling simulation. So you compile it, and you plug it into Verilog, and it's working. And it's available in Verilog-A. And what we miss all the parameters, and we miss these modules in Verilog-A. So part of the effort that we do in my lab, we try to write modules for Verilog, for biology, electrochemistry, optics, and other things. So you can design it. 3 electrochemical cell I'm going to do it today, and we simulate also kinetics and mass transport effects, everything in one run. So the biochemical sensor that we do, this is the, sorry, it was running fast. This is the PhD of Richard Pandi, which is now a professor in Calgary. We demonstrated it 6 years ago. This is a plant-based sensor. And what we have here in the plant-based sensors, we have the plants, which are the sensors. We have the substrate. We are generating an enzyme, and the enzyme generates a protein, and the protein generates a signal. It's not relevant to much of the talk today, but the idea, we need to detect electrochemical signal. So, which means we apply voltage, measure current. We do pronoun parameter. Challenge, functional plant sensors are induced current in the range of 0.1 milliamp per second. The signal is very noisy. We need amplification. And interfacing with VLSI is an option. And the idea is that the plant-based electrochemical sensor, we have, I don't want to go through the whole theory, but practically we are generating a product, and the main equation is the Michaelis-Menten equation. So this is this very famous equation. You have enzyme to substrate, react an intermediate, you generate an enzyme and a product, and you oxidize the product on the electrode, generating a current. So this equation, this model, you can write the rate equations and simulate. So the theory is that you have a reaction. The pointer is kind of practically not working, but the idea is that you have the reaction and you write the Butler-Volmer equation, which means if you know the concentration, you can calculate the current. The problem is that all these concentrations, COx in the bulk, C-rate in the bulk, you need to calculate them because they're changing with time and also changing with distance. And they're all being reduced or oxidized in the electrodes. So if you really want to simulate the current, you have to solve basically the transport equation, Fick's law, and the diffusion equation. And I will not go through this basic, but the idea is that how to do it in Verilog-A, how to solve partial differential equation using a software that was designed to solve VLSI hardware problems. We found out the improved version of Verilog HDL taking care of analog functions, and also it behaves like a SPICE. If you remember, some of you remember the SPICE program. This is the engine of modeling, of simulating circuits. And in SPICE, you have all of these rate equations, which if you ever wrote, I was in Berkeley as a postdoc writing codes in Fortran for SPICE. So if you know to do it, it's very simple. So Verilog math functions are very similar. They can use in place of constant expression that supports both integer and math. And you have numerical model can be conceived. But the only problem, you have to write it yourself. Because the people who wrote this program never thought about using it for biology or for electrochemistry. But this is a nice project for students. So what you do, for example, you can write the final difference equations using Verilog-A. How to do it? You just write, you define, for example, this is a model. If you look at it, this is a model of one electrode in a solution. And I apologize, the pointer doesn't work. So this is the electrode. This is the solution. You discretize the solution. You write the difference equation. If you look at the top, this is the diffusion equation discretized. Then you write the boundary condition. The boundary condition, which means the current going in, change the current going in by the reaction is equal to the current, which is by the diffusion. This is the boundary condition. And you write it in the difference form. And this can be written in Verilog-A. So the idea is very simple. If you look at the flow diagram, you have the special distribution of the species concentration stored in arrays. The concentrations are updated at every simulation time point, and the computed redox current and concentration profiles exposed as output of the model. So you can actually, what you are doing practically, you're solving like from basic diffusion equation and transport equation. You're solving the electrochemical problem using Verilog. So you write this subroutine. So what you do, you put this subroutine, you compile it, and if you look, this is, now you plug it into the analog simulation. Now, this is a potential stat that we designed. It was similar to other potentials published in the literature. What we do here, this is a potential stat we designed. The amplifier itself, we designed the amplifier. It's a sub-threshold CMOS amplifier. We work in the sub-threshold because we designed this for IoT, so we have a very low power device. Again, it's another lecture, but the amplifier there is very interesting amplifier by itself. It's a folded cascade sub-threshold amplifier. I'm not going to show it today, but you have to trust me that everything here was CMOS designed. I'm showing just the highlight of the talk. So, and the output is going to a current voltage converter, the output over there. By the way, if you notice, I'm running here between 0 to VDD, and the reference is at half VDD. And the reason is because I can do reduction and oxidation. Because if I go above half VDD, it's a positive working versus reference. If I go below half VDD, so instead of going between minus VDD to plus VDD, I'm going between 0 to VDD. I'm using a single battery. Also to save space, to save time, because everything, this is implemented in a biochip. So what we do know, this is the setup. The Verilog-A model exposed as a black box component to the Cadence Virtuoso design. Simplistic potential stat is designed. Op-amp and voltage source are the op-amp and voltage sources to the supply input. The MOSFET control pass-through is going between the working electrode and the counter. The transient simulation performs. And this is what you find out. You find out, surprise, simulation looks like the measurement because we took the data from the measurement, we did the measurement, and we simulated it. And if you, this is for electrochemistry, this is like the trivial measurement. This is cyclic voltammetry. So we can simulate cyclic voltammetry using Verilog with a fundamental CMOS design with all the bells and whistles of this folded cascode device. So we do the layout, and the student push the button and run the simulation. So we can run the cyclic voltammetry. We can do also, but it's a bonus. I can also generate like concentration versus distance. So we put another GUI to make a window so we can actually look at the solution for the electrochemistry, so we can figure out a little bit. We are working on other electrodes now. We are doing like four electrode devices using redox cycling, and we are working at the other boundary conditions. What I demonstrated today is a very simple device, only one electrode, infinitely long, but we are writing subroutines for other electrodes, so everything looks fine, but again, it's not an ideal system. The temporal and spatial resolution of Verilog model determine the accuracy. There's a trade-off between accuracy and simulation, as you know. It has to be improved. Verilog-A use explicit methods, so I cannot do implicit modeling, so I have to sometimes to go around when I do the simulation. So if somebody can improve this, this will be really nice. So more comments. The mathematical framework is incomplete in Verilog, so sometimes we have to go like to a little bit not the best way. And the dynamic time steps that are determined in biosimulation framework are incompatible with implicit methods, so it's a problem, which means, as I told you, we could do better. Verilog-A can be used to simulation. Diffusion modeling has been done. Next is we are going to add convection and other sensors. And acknowledgement, Israel Innovation Authority, Israel Science Foundation, Ministry of Science and Technology. Thank you.